So I should warn you that my talk is technically oriented. I'm not really going to talk about agribusiness per se. I'm going to talk about work we've been doing in making robots endowed with enough capability, enough smartness to let them understand visual imagery and do things on their own. And I'm going to focus primarily on the technical issue, not on the deployment in real applications. I happen to be the director of the Canadian Field Robotics Network, which is a network of people working on robotics for marine applications, aerial applications, terrestrial, other domains as well, all outdoors. And that's really the key focus of my talk. And so I'm going to talk today about robot observers. That is, systems can look out in the world and make observations on our behalf. They can monitor, assess, manage natural resources of various kinds for us out in the world. Of course, agricultural resources are a #1 kind of application domain for this. And field robotics is the class of robotics applications that focuses on robotics for outdoor environments as opposed to office navigation or in our cities. So monitoring is a domain of applications with tremendous applicability, of course, besides just agribusiness. And I'll mention, of course, in the wilderness, in the outdoor environments, that includes surveillance for diseases, for insect infestation, for inappropriate use of resources by human beings, search and rescue, a wide range of problems, all characterized by the need to assess wide swaths of land and understand what's going on within those areas of land. And often that assessment is done using computer vision, that is imagery of some sort. Maybe optical imagery, maybe other kinds of multi-band spectral imagery, but nevertheless imagery is the underlying sort of theme that leverages a lot of these applications. And that's really where my talk today is going to focus. So before I start talking about how we're going to do robotics, I just want to sort of recap what I mean by a robot. And so a robot, I think, in its purest definition, is a system that embodies 3 kinds of capacity. The ability to observe the world, that is, look out at the world, the ability to make a plan based on those observations, and then the ability to change the world, to actually do actuation and move about in those worlds. So if we think of that by analogy to human beings, you know, the thinking part is essentially what we think of as our brain doing. Of course, our brain does all of these things, but the ability to formulate a plan. The observation of the world would, of course, be our eyes, and the taking action would be the equivalent of our hands and our feet moving about in the world. And we need all of these 3 together to sort of envision the purest form of robotics, I would guess. Of course, many robotics people work on sub-elements of this grand vision. But notably, the problem of making observations with our eyes, that is, making measurements, is intermediated by one further step, and that's the need to make an interpretation of the imagery coming in. About 50% of the cells in the human brain are tied up with the process of taking the imagery that comes from our measuring devices, that are our eyes or our ears, and interpreting those signals before we can formulate a plan. And so that problem of interpreting visual imagery, understanding what we're seeing in the scene, I think is in many ways one of the key elements of achieving a vision of robotics that can function in our world. It's also probably a key element of building systems that we can use to understand our own functionality as human beings in the world. And so one issue that comes up occasionally, people ask me about where are all those robots that we were promised when we were children? Where's Rosie the robot and R2-D2 and C-3PO and the things that we imagine would be the robotics revolution that we should be living in? And you know, people think maybe they're parked beside the flying cars that we also expected. I don't think we're going to see flying cars in the immediate future, although there are companies working on those, amazingly enough. But robotics, I think, is coming at a much faster pace, and I think we're probably all aware of that. A few years ago, robotics was characterized by slow, clunky, arguably stupid vehicles that really couldn't function very well. The robot on the left, Shaky, that's one of the first mobile robots developed at Stanford Research Institute in the late 60s, moved about 1 footstep every 15 minutes and took very low resolution images and could really not function well in the world. So what became of these things? That's really the focus of my talk. And I guess one question is the promise of robotics as expected, as delivered, really arriving on schedule? And are we expecting too much from our robotic systems? And so those are questions that we can talk about later on, perhaps. I think today, the realization of robotics has in many ways shown up in many ubiquitous devices in our world. And the ones that characterize that best are our cell phones. These phones include cameras, GPS units, speech input. They can vibrate, they can shake, they can talk back to us, they can make plans, they can tell us when to get to places on time. They're in fact completely filled with technologies that were developed from this vision of robotics and the robotics world. And so in some perhaps simplistic sense, telephones today are already the realization of robotics coming everywhere in our world. And I think this notion of robotics imbuing the world that we live in is being realized in many other ways. In our washing machines that know how to wash things appropriately, in our vacuum cleaners. This is a microwave oven that I have at home. It's painfully smart in the sense that I can take some arbitrary thing from my fridge, put it in the oven, and press a button that says cook. And it knows how long to cook it, whether it was frozen or not. It measures the humidity, the weight. I don't actually know what it's doing, but it makes some plan on how to cook that thing. And then at the end, it goes bing and says, enjoy your meal. It really is a robot in some very literal sense of the world. The one thing it lacks is the ability to walk around and smile at me. And so many other applications already exist today of robotics. Exoskeletons that allow people to move more quickly. Those are largely confined to the military. Things that can pick fruit. Things that can explore Mars. Things that can actually interact with us as if they were our companions. A huge range of things. The success of the Tesla automobile is largely a result of the tremendously automated factory in Fremont, California that takes chunks of aluminum in and, roughly speaking, turns out cars as a result. And it uses very flexible automation to do that. And I think the self-driving car is probably the poster child of the robotics revolution. Every time I use this slide, I realize I have to update the number that's on the bottom. I think these automated cars that Google's deploying, they have about 250 of them on the road. They've executed about 1.6 million kilometers of road by now, and they have much better accident rates than most young drivers would have at the same level of performance. And so this stuff is really coming. It's really ready for prime time. A lot of the challenges with these vehicles are basically the legislative and human interaction aspects that will let them go. And so one thing I guess that you should all wonder about is, would you trust a robot car? And would you trust a robot piece of farm equipment to run around on your property unattended? And I think one of the striking realizations for me sitting in that Google car is how quickly I became completely bored with the process. It drives perfectly. It's basically boring after the first 5 blocks. Of course, if you're a really nerdy guy like me, you spend a lot of time looking at how it's doing that. But really, the driving experience, people get acclimatized to that very, very quickly. And so, but on the other hand, we should ask the question, can this Google car learn about new roads as it drives upon them? To what extent is it able to adapt, and adapt especially to the visual experience that it encounters, and how does it cope with surprises? And that's the thing I'm going to focus on most of all. So see, these are some of the robots we work on, things that fly, things that swim, things that walk on ice and snow, things that roll around as teams, things that swim through the pool or through the ocean. This is footage from a completely autonomous unmanned air vehicle. And so here it's flying along some chunk of coastline looking for interesting biological phenomena of some sort. And it's doing it without any human intervention whatsoever. No GPS waypoints, no person driving the vehicle. It's fully autonomously choosing where to go based on the visual feedback it's receiving as it flies. Sadly, this class of research is very hard to do in North America. In fact, this project that I was involved in has been largely abandoned because of the legislative restrictions on doing the work in North America with fixed-wing aircraft like that. But those vehicles nonetheless return enormous amounts of data, whether they're on land, underwater, wherever. And it's how to manage those huge data streams that I think is the focus of what I want to talk about. What are the good bits of the data? What are the important parts? And what are the important parts in that data stream that we didn't expect to find initially? Because one of the huge aspects of having a person in the loop with these systems is that it can detect anomalies, weird things that you didn't think were there. And that detection of novelty is something we really have to be aware of. So if we think of robots that go out in the world and make observations for us, I think there are 3 key tasks I would suggest they have to deal with, the observational tasks. The first is detecting familiar things of interest, whether they're things on a production line or things from the air. And that problem of detecting familiar objects, I'm not even going to focus on today, because I think it's relatively well-developed technology. I'll just illustrate it very briefly. But I think the second 2 problems, coming up with a short, terse summary of the data they collect, and then finding anomalies within those data streams, those are tremendously interesting and difficult problems. That is the problem of what did you experience today as you went out and did your work as a robot? And that's really the issue. So recognizing familiar things, whether they're barcodes or shovels or pictures of machinery that we have, those things we can basically build simple machines to do. And when I say simple, I mean gigantic computer vision machines that weren't possible just 5 or 10 years ago, but they're now thought to be relatively known technologies. And even things that are only somewhat familiar, funny looking barcodes that don't quite match our template, or snow shovels. That thing on the bottom left is a snow shovel, very familiar to Canadians, probably less so here. Or vehicles that don't actually fit the normal template. That stuff we know how to deal with. The question is, how do we get to do robots to look for more than just pre-programmed things that people have said a priori are of interest to us. And so the idea of building an intelligent explorer that can move out in the world and assess our assets, and those assets could be visual assets from the air, or they could be server stacks in a serving farm that have to be working according to some sophistication. But finding and selecting the interesting things, that's a key element. And this problem of detecting novelty, it's a fundamental attribute of just being a human being, of being an intelligent agent on Earth. Children learn to be surprised by novelty at an extremely young age, to find things that don't fit the template of what they expect to see out there. Likewise, scientific discovery is leveraged by this. If you think of the discovery of the X-ray, for example, that was discovered by somebody noticing that there was a phenomenon in the world that didn't fit the normal template of how light should behave. It could pass through objects, and there was something there to be discovered. And it's a recurring characteristic of scientific discovery. If we think of environmental stewardship, a big aspect of environmental stewardship is noticing when our environmental parameters are out of whack. Those could be good things, often they're bad things, but detecting the anomalies, the things which are atypical, is a key problem, and even humor, that's a real fish. Even humor is directly tied to the notion of novelty and surprise in the world. And so I'll talk a little bit about how we can get robots to detect surprising events. And so I want to talk first, before we talk about surprises, I want to talk about building summaries. That is building a synopsis of what we've seen in the world. So let's imagine we have a robot, it goes out to the world, and it sees this cartoon-like set of images that characterize its voyage through, I guess this would be Auckland harbor area. So it saw some water, it saw a lighthouse, it saw a ship, and it saw some land. And a good summary of that might, for example, be one photo, the 4 orange boxes that characterizes each of those 4 types of terrain. And so that's the kind of thing we'd like to extract as a summary. And this notion of a summary, although I'm illustrating it in the context of images, again, this could be applied to other kinds of data domains as well. And so one thing we might ask as an aside, and a question I won't answer, it's because it's a very technical question, is what's a better summary? The average experience that you've had, or the surprises and the weird experiences you've had as you go through the world? And I'll leave that for you to think about. Typical or the surprising? And how do we, so the question I want to address is how do we characterize and compare images? I have pictures taken by my robot out in the world, and I'd like to somehow build a synopsis of those images that lets me organize them into groups, summarize them, and then find the things that stick out. And so I want to look at how to do this problem, practically speaking, by drawing an analogy to text documents. So if we think of a typical newspaper article, one approach to handling newspaper articles is to just look at the distribution of words in the article. This is referred to a bag of words approach. So we might, in this article, have the word animal 6 times, and the word costs 4 times, and fertilizer twice, etc. And so that distribution of words in the article turns out to be a very powerful way to organize documents and put them into topics, into classes. And so, for example, on the left, we might have an article about the future of agriculture, and it's characterized by the occurrence of words like future and farming and agribusiness and using. And we might have an article about Canadian robotics, and that has words in it like robot or robotics or space or machine, or if we're lucky, maybe McGill, because it's Canadian robotics. This notion of organizing our data into a statistical distribution with respect to what we expect to find, that's a tremendously powerful idea, and it can be applied to the world of images. So if we take pictures and we have a way of letting our robot, our computer system, find points in that image that are of interest, we can then organize those points of interest into an analogy of words. Little bits of the image that occur periodically, statistically, in different kind of categories. So if we have pictures of airplanes, we regularly see little bits of stuff that look like bits of airplane. And if we have pictures of faces, we see little bits of face. And if we have pictures of leaves, we see little bits of leaf. And if we have acoustic signals coming from some auditory domain, we'll see little bits of sound that tend to reoccur. And if we have signals from a server stack, we'll see CPU cycles that tend to reoccur. And so this notion of making visual words, by analogy to English words, then allows us to use the same kind of ideas to organize these things statistically into groups and categories that we can use to let our robots understand their world. And so we can take this idea of organizing things statistically and build a robot system that flies around the world, makes observations, builds a summary, and when it sees things that are surprising with respect to that summary, that is, we see a type of document, a type of image that doesn't fit into our known classes, we add that to our summary. That has become a novel thing. And if we don't see that, then we can reject that image, or we can add it to the list of things that we've seen that are familiar in that particular class. And so applying this idea, we can call this the vacation snapshot problem. This is the problem where Greg Dudek goes to Auckland. He's not on vacation, of course, but he's taking photographs, and he'd like those photographs to summarize his visual experience with one photograph in each class. Not too many in any one class, and leaving no classes out. And so now we can take this idea and we can apply it on that UAV that I illustrated a minute ago. This is a hand-launched little UAV. And here we're seeing a live view from the camera, of course, a canned live view coming in the upper left. This is about 10x real time. And we're seeing this vacation summary. It's tasked to find 6 photographs that epitomize its voyage. And right now, initially, it's only seen city scenes, so all of the pictures are of city. And as time passes and it sees more and more content, eventually sees some ocean, some beach, that repertoire, that summary of what it's seen becomes richer and richer. So it basically summarizes the extent and the richness of its visual experience through the world. And after a certain amount of time, it's seen a little bit of forest, a little bit of water, a little bit of beach, a little bit of city. It's basically characterized the set of things that it experienced as it flew through the world. So some of our work is in the marine environment. It's an environment of particular interest to me because as a roboticist, it kind of has all the richness of almost any domain one might work on. It has full motion in all dimensions. It doesn't have communications. It's GPS denied, so you have to decide for yourself where you are and what you're doing. And it's tremendously important in by almost any metric we might offer. Biodiversity, economic impact, climate, the food web, etc. And it's in tremendous peril right now. So it's a good surrogate for many of the other applications we might like to work on. And we do work in that domain using a vehicle like this. So it's an amphibious vehicle. It can walk and it can swim. It doesn't go very, very deep. It only goes to about 130 feet, 30, 40 meters, typically, because a lot of the time we're using graduate students as the surveillance operators to basically monitor its performance. And it allows us to build summaries of the underwater environment. And in particular, we look at summaries of coral reef environments, so we'd like to assess the health and diversity on the coral reef. And so here we're seeing the beginning of that process, an image coming up in the upper right, a set of these visual features below that, and then a summary of its experience. And initially that experience is very minimal. It's only seen a little bit of terrain, but over time that summary grows in terms of its richness and diversity, capturing all the things the robot has seen. And so eventually it's found fire coral, it's found finger coral, it's found bare rock, sand, all of the things that characterize the coral reef on which it was deployed. So once we can summarize their experience, then we can actually go out and try to seek novelty and seek particular kinds of things within that environment. Seek out the new and interesting things in that marine environment or any other. So here's an example of a robot that's being deployed on the reef. A human is actuating it with hand gestures, so it works as an assistant to a diver in this particular case. And it's going to swim over the reef and find novel things on that reef based on this notion of summarization and finding things that are unusual. So now instead of looking at entire images, it's looking at little pieces of the images, and at every moment it's finding the red dot in the image is the most interesting thing in that particular image. And that's driving its desire to explore. It's trying to find the thing within the image which is the most interesting, and it's going to head in that direction. And so initially it explores this coral reef. It's a very unhealthy coral reef, incidentally, mostly rock. But it explores this relatively thoroughly. And at some point, it's seen enough of this reef to become fatigued with the notion of a reef, and it's going to head off in some other area. Initially, it avoids the sand and stays on the reef because the reef is the most visually diverse and interesting domain it's experienced so far in its lifetime as a robot. So we can see it doing a circumnavigation of the reef environment, exploring the inside, exploring the outside. And one of the metrics for performance is how much travel did it have to do to encounter everything that it could have seen in the environment. Eventually it leaves the reef, moves into the sand, and it encounters a diver. And then once it sees a diver, it explores that diver, taking images of the diver, and then it notices the bubbles. Like any novice scuba diver, it starts looking at the bubbles, observing the bubbles that characterize that environment, basically finding everything in that environment that you might say is an interesting different kind of phenomenology in the visual domain. So here it is examining the diver quite thoroughly. And there's the bubble, it's seeing the bubbles. And eventually it gets tired of the diver and moves off and explores further parts of the reef along the ocean bottom. So the interesting thing here is that without any human intervention, we have a system that can go out and explore a novel world and fully examine the things that characterize it, the things that make it up, both the good things and the bad things, and come back with a report on what it's seen. So once we've got the ability to autonomously explore an environment and characterize what's in it, we can use data about what we care about, in this case, annotations by a biologist on live coral versus dead reef, and we can learn the characteristic of those images as well. And that's the problem I referred to earlier on as being relatively straightforward. So we can train the system to say, these images are dead coral, these images are live coral. While you're exploring a reef and finding everything unusual, we'd also like you to build a map of the reef and tell us where the healthy parts are and where the unhealthy parts are. And so here's an example of a mosaic of a reef on the left-hand side, just a pictorial mosaic collected by the vehicle. And on the right-hand side, we're seeing a map colored in red of where the coral is alive and where it's not so healthy. And so we've also done a survey now of the reef in relatively efficient time, relative to what it would take a human to cover this or to do it with some other kind of vehicle. So this thing ties together the notion of exploration, summarization, the detection of novelty, and full autonomy in a robotic vehicle. Here's another example. This is data collected from colleagues at Woods Hole. And so this is at about 2,000 meters under the ocean, using a vehicle that looks something like this. So the thing drives along the ocean bottom and looks for phenomena of interest. Again, finding anomalies is tremendously important. Right now they have people who sit in rooms looking at video for days and days at a time. And so the ability to look at this video automatically is tremendously important. Here we're seeing the robot detecting crabs on the ocean floor, and it's basically building a survey of the density of crabs along some region of the ocean, which is of particular importance to the biological team. So I guess what I've talked about today are robots that can not only do rote tasks, but they can discover new knowledge, new things in the world, and they can alert us to the unexpected. So these sorts of robotic vehicles aren't going to be deployed without a human to intercede and look at data at the end of the day, but we don't want humans that have to look at the data every minute of every day, but rather they have to look at the data in terms of its highlights and its anomalies and the key features that characterize what's been going on in that scene. And that's where I'll conclude. I'll pose a few questions that you can think about later if you're interested. And that is, how do we match this intuitive notion of being interesting to the things that the robots find novel? So if the robot finds something novel, is that what you care about? If we're going to have robots that explore the world autonomously, how do we make sure that the things that they explore match our needs for what we care about in terms of achieving some goal? And that's another problem that I haven't talked about. And how can we combine vision with other kinds of sensors that guide that exploration process? And a ubiquitous problem that comes up all the time is, will robots become dangerous? You know, where's Terminator? Where's the amphibious in this amphibious robot? I haven't talked much about that. And how difficult is it to control a robot of this complexity? And in particular, how hard is it for a human to moderate and control its behavior? So none of these questions have been addressed explicitly, but we can talk about them later if you're interested. And that's where I'll stop.